Perfect. Thank you so much for that wonderful talk, Dr. Clement.
You're welcome.
As you said, we'll be moving on to the Q&A portion of today's webinar. If you would like to ask a question, please use the Q&A feature, not the chat. So let's get started. First question, what did you say the max travel distance was for the neuroglider?
For the standard neuroglider, it's a 12, I should say 10 millimeters to be safe. I think you can go a little bit plus or minus on either side, but it's a centimeter. So it's more for surface cortical kind of insertions. But the Micronics, the place where we get the linear stages from, they make a number of different sizes. So depending on what the needs may be, it's relatively easy to adapt those different stages because it's the same code. The lab view that's been written out to communicate with it shouldn't need changes.
Great. Next question, an attendee notes, fantastic device, damage due to guide tubes is a prevalent issue in the non-human primate electrophysiology and was mentioned during the last talk by Dr. Fries. Unfortunately, the current device is too large to fit in current NHP recording setups. Has there been any progress towards designing a smaller version of the actuator?
Not yet, but it's something we can consider. And I think it probably should be possible because the this actuator is capable of doing much higher power. So we're probably, and many times we don't need to use the full capacity. So we just have to look, because the design of the actuator can also affect the frequency as well of the oscillation. So it would require a bit of a development to explore, but yeah, and we'd be interested in talking to other primate users, like what are the needs. I know some people need to be able to sterilize everything, and whereas rats, it's a little bit easier to get away with wiping things down and such. So some of those conversations are ongoing, but if we can understand those needs a little bit better, we might be able to re-engineer something that would work.
Great, thank you. Next question. Do you know if the vibration itself could affect neuronal excitability, for example, through mechanosensitive channels?
I don't know for sure, and I don't know. I don't think it does. Not in an adverse way, and not a way that seems to maybe negatively affect their survival and stuff. At least from the studies that we've done. But it's an interesting question.
Okay. What parameters of the probe, such as thickness, smoothness, sharpness, or brain thick pia vessels, impact improvement provided by vibration?
I know that the tip shape can play a role in the overall length, but haven't explored, in a we're kind of gathering information as we speak from all the different probes we've done, and trying to organize it in a way that would maybe allow us to see patterns. But at this point, the ones that have kind of like that are like, for instance, the V probe worked really well, but and then the 1S probe that we've tried, it improved it as well too, but it seemed like the V probe was a lot better. So, but yeah, I guess that's about all I have to say.
Okay, great. Next question. How does damage of vasculature affected by ultrasonic vibration compare to very slow linear insertion?
I like the one slide that I showed earlier where we kind of looked at that was with TDT arrays, and I have to go back notes to see about other probes that we've tried in vivo, but the vibration can actually tend maybe even to lessen the amount of bleeding that happens during the insertion. I think it might tug at the tissue a little bit less and enable the vessels to kind of presuming, but that thought is that maybe it would help the vessels kind of glide around the probe a bit better. But the only time we saw maybe that it would impact bleeding was early on. We had a situation where sometimes there'd be some out of plane vibration that would occur, depending on the lengths of the shanks. And if you're vibrating too soon, like one thing you can do is delay vibration until you're touching the surface. That tends to really, if you do see some of the out of plane vibration, that will halt that. But provided that's not going on, it seems to not adversely affect bleeding.
Great. Next question. Have you tried this with syringes or cannula, for example, Hamilton syringes?
Interesting. Yeah, I tried. It was sort of a prototype kind of thing. We'd made a different ultrasonic horn that could connect to a Hamilton syringe, like through the I can't remember now. It's been a little while since I've tried it, but we could get some vibration transferred to it. And it wasn't. We didn't expend an extensive amount of time looking at it, but it was definitely a lot less than like in doing insertions in the agar. We couldn't see as much reduction of force in that kind of setup, but it's something that I didn't spend extensive time with yet. And based on kind of what we've learned over the years, it might be worth revisiting again.
Okay. Next question. Does the fluid leak into the interface between the probe and the brain lead to shunting of the signal, at least in acute conditions when recording is started soon after insertion?
I haven't observed that. We've done, I think I mentioned that one slide there, and that one that we penetrated through dura. Being able to make recordings right after stopping the turning off vibration and stopping the insertion, mainly just because there can be a little bit of noise, more electrical artifact when the stage is moving and or there's the transducers active. So, but we can, immediately turn off and really not have to wait any time at all and get recordings. And as well as, sometimes our best recordings are post-op when we're doing a survival animal, being able to get recordings like right at the end of surgery. So I don't think, fluid ingress is an issue, at least any more so than, any of the other uncontrollable variables might affect that in a standard insertion.
Is there any reason to not use a higher power vibration?
I don't know yet. I mean, I guess there could be. This is more like we've been working on a similar device. It's much more higher power for going into bone or the penetrating it into the epidural space for delivering epidural needle. There you do have to be cautious of possible heat production at the point, at the tip where the vibration is, if you cranked it up too high. So that would be a potential concern, and or potentially damaging or loosening either breakage of the electrode or loosening of components in the electrode or in the coupling chain. So we always that's why I kind of try to figure out at what point does the power saturate, because you're not going to get much more benefit from going higher power. So I guess that's what it would be. It seems to be kind of a limit at some point. More power doesn't give you more performance. So it just seems like a good idea to not go up too high.
Great, thank you.
Mm-hmm.
Next question. Could you tell us how you plan to extend this approach to floating arrays?
Yeah, can I share a screen?
Yes, you can take over.
I don't know if I do. Oops, gotta pull my. So let me see if I can find. Here we go. So this was our first attempt at it. Oops. Is through an actuator that we've called the tweezer horn. So it rather than having the lure lock connector that's on the end here and the normal coupling chain that's used to get to the transfer the vibration, the horn itself just extends out, and then we had a tweezer arm that's held in contact with a matrix array through the elastic O-ring. And the idea is that, if you get this machined right, you can have very limited gripping around the outside, and you can get enough vibration transfer. Basically, the tweezer arm is there just to kind of hold the implant tight against the vibrating portion, which is the metal horn here. And then it would implant, and then you do the implant, and then you would clip away, shown here, the O-ring to then release the device. As you might see, this has got some usability, concerns, and would take some practice to get good at. So we're actively looking at possibility of using a vacuum type or a vacuum connection to hold the array in enough to get sufficient vibration to it. So it's actually something that's actively being pursued right now on our phase 2 grant in the BRAIN program. So more to come on that. But I think the next slide, there's one video that kind of demonstrates the concept of that prototype. We'll see on the right side again is a vibrated insertion. This one is in actual time, so it's a little slower, but you can see there's a lot of vessels around there. It's able to glide around them. So that slow of approach might not work well for a primate, for instance, right? Or they need to possibly time the respiration, so there's not as much brain pulsations if you're going to do a slow insertion like that. But it's an interesting idea.
Okay, great. So we do have quite a few more questions. Are you okay to keep going?
Or... Yeah, it's fine.
Okay, great. Let me share my screen again. Okay, next question. Do you have any data or intuition on whether or how the design and stiffness of the array would impact the penetration, such as the Utah array compared to more flexible arrays?
Yeah, we've had and haven't been able to completely understand it, but the BlackRock array has been one that's more difficult to get to work well. Like we get, in agar model, 50 to 60% reduction of force, maybe 40%. It's just not quite as powerful. And I don't know if it has something to do with the, my intuition is it's something to do with the kind of the shortness of the probe, or each of the shanks, and the fact it's kind of like pyramidal shaped, that it doesn't seem to be as effective in getting vibration on the shanks. So versus the matrix and all the neuronexus probes that we've tried, it works really well. And it, that is one difference, is that it is the same material, silicon, but something to do with maybe the more planar geometry. The vibration seems to help a bit better.
Okay. Next question. Does it work on acute recording, or is it just designed for chronic recording?
No, it should work for acute recording. We've had success getting recordings immediately after insertion. So should work.
Okay. Which direction is the ultrasonic force giving, vertical or parallel to the probes?
It's designed to be primarily axial, so in the direction of the advancing electrode, it should be going that way. But there is probably some, we've seen it on some probes where there can be a slight out of plane motion, and in fact, you can feel whenever you're vibrating something along the edges, it will. You can feel a smoothness, like if you're measuring or feeling the vibration on a long needle or something, you can feel it kind of it becomes lubricated in a way, and then there are also nodes along the way where if you had like a sometimes what we'll do is take a fine hypodermic needle or just a wire. It can kind of the vibration actually encourage the wire to go to a certain length along a needle and kind of stay there. So kind of rambling a bit, but there's it is primarily directed, the way the actuator does it is in the axial direction, but can't rule out that there's some at least negligible amounts in the out of plane. But if typically what we've observed with some probes is whenever we've seen some out of plane vibration, if it was too much visible, on the microscope, you could delay it until the probe is engaging the tissue some, because it really is, it just, once you kind of change the state from being a free end beam and you start to restrict the movement a little bit, then it really will knock off the out of plane. Another thing I was noticing with the just kind of fun games playing with the qualia probes with vibrating, if there was I think there was one that was the longer length probe, a 5 millimeter, and it seemed to have a lot of out of plane at the higher powers. You could actually just add a little bit of a drop of fluid onto the end, and that seemed to really channel all the vibration in the axial direction, or at least restrict the out of plane movement. So probably just the extra weight or mass of the fluid being on the tip tended to knock that down. So so even when there's, you observe a little bit of out of plane vibration, there's not much force or momentum behind those out of plane vibrations that I can do. I think that.
Okay. Next question. Could the ultrasonic actuation damage the fine metallization or electrodes on a probe?
I can't say I've tested every probe. I know that was a concern when we first started trying it with neuronexus probes, is I think I don't know the history behind it, but there was some concern that vibration would break the shanks or shatter it. Maybe it's because of doing ultrasonic cleaning that would happen, but that's not what we observed. Being able to get recordings and as long as the power level, there was one instance where we were working with a matrix array early, and the way that we had the control box set up is it would normally be at a really high power and then sweep down to a low power. We had one problem where we shattered a dummy probe because the vibration was too high. But I think I talked myself away from the question again. Can you remind me again the question, actually?
Yeah, of course. Could the ultrasonic actuation damage the fine metallization?
Oh, okay, right. Yeah, but I remember what I was gonna say now. We did testing of probes before and after, like a couple pieces of evidence. One, we did early on testing of the neuronexus probe before and after, and didn't see any changes in impedance after doing a number of vibrated insertions in the agar models, and the fact that we're also get recordings post-op, and so I don't think there's I don't think it affects at least in those silicon probes that have like the different laminating areas. And we've also done some polyimide probes as well, and those seem to hold up fine as well.
Okay. What range of oscillation frequencies is most effective?
Just to clarify, the actuator itself works at around, it has a resonant frequency that can change just a little bit depending on what's connected to it. But the control box is designed to find out what that resonant point is, and that's it's got a way of determining that based on the impedance signal, that it will always be vibrating at resonance, and that's typically in like the 22, 23 kilohertz range. So and that's based on the transducer design that we have had for other projects, or had a history on other projects, then it got adapted to here. But typically that is our rule of thumb is you want to have something just a little bit above the audible range, so it's not too annoying, but not so high, because at the very high frequency, we have sometimes seen on other projects that the higher frequencies can produce more heating, but that was on another application, another type of probe, so you have to be careful of transferring that to this application. But that's the general feel. Because I think you need also at the higher frequencies of oscillation, you'd lose some of the displacement, and which I think might be important in this application.
Okay. Next question. Is it possible to insert a probe with the help of ultrasonic vibration without the opening of Dura matter?
Yeah, that's the I'm drawing my that'd be the treasure, or the goal. I haven't done extensive testing with at least I should say it's no problem with some of these probes going into rat dura. Pig dura is much more challenging, and I think it might require some more complicated insertion schemes. So you might need to, and this is where we need to do the optimization and playing, doing some more testing and figuring things out. But possibly stepwise insertions where you're letting the vibration work for a bit, maybe rather than just a straight on insertion, may work better. Also coupling that with additional fluid. I had, again, it might have been like an N of 1 or so, but I was trying to get through one dura, and I seemed to apply some saline right at the point, and it was either coincidence or not, but then it popped through. So it gives me some thoughts for like how we can move forward and not giving up on trying to get through dura yet, but some different things we can try. I know there's some folks that would like to be able to do that.
Okay, great. Next question. Has anyone used your system with carbon fiber microelectrodes for FSCV and dopamine measurement in the NAC?
Not for those applications, but we have done, we did kind of a pilot study with some carbon fibers, kind of in an acute setting. And we've been able to, these are some like out of University of Michigan. We had some success getting even single carbon fibers through a rat dura. So yeah, I think there's a lot of potential there. And that's actually one of the things we're planning to do as part of the brain phase 2 is sort of do a more in-depth study of inserting carbon fiber arrays. So more to come on that.
Are you gathering histological evidence that the parenchyma is less damaged with this approach?
We have very limited histology, partly just due to we're a small company and we always bite off more than we can chew, I think. And it's difficult to do the number of animal studies that you'd need to do it. But we are, like I mentioned, may have got glossed over, but partnering with a group at UNC who is going to be doing that for some polymer probes that we've been testing with, and also TK Kozai at Pitt, who will be doing some histology for us as well. And we have more of that planned with some of the special arrays that we're going to try inserting on our phase 2 project that's active at the moment.
You had mentioned inserting Polymide probes. How long and thick were those? And were they hanging down like the shape memory polymer probe?
Yeah, they basically were very similar. I think the length that we'd been working with, a probe that was 10 millimeters long, I think out of the UNC lab, that's what they were using. I'm trying to think. There's another style that we've been working with. I don't remember the dimensions of it right now, but I want to be the shanks were in that 5 millimeter to 10 millimeter kind of length. And that particular configuration I'm thinking of was more like on the end of a ribbon cable. So the technique we used there was like like the H style probes from NoNexus, where the probe is on the end of a ribbon cable. We would bond it to some peg at the end of a flattened needle coupler, and that's worked pretty well. Okay.
One last question. Do you have a Neuropixel adapter?
Not yet. I would. Yeah, it's probably worth reaching out to a lab that's using those, and/or Neuropixels themselves. We just haven't done that yet.
Okay, great. Well, that was our final question. So thank you again, Dr. Clement.
You're welcome.
Great. And thank you to everyone else who attended. If we didn't get to your question, we'll contact you directly.
Okay, great.
And make sure to catch the next installment of our webinar series, which is next Wednesday at 10 a.m. This was the talk that was supposed to be last week, but got postponed. Dr. Ariana Andre will be giving a talk entitled How Cortical Population Activity is Integrated for Visual Perception and Optogenetic Approach. We'll catch you next time, everybody. Thanks.
Thank you.